Hello, I'm Dave Tabb, and today I'd like to walk you through how we interpret the search results that come from TopPIC Suite when we analyze data sets of shotgun proteoforms for top-down proteomics. I'll be using as my example three raw files that I've drawn from PXD019247. That is a set of E. coli lysates used for instrument tuning, and in this case I'm just choosing three of the raw files from it. It could easily be data from any other experiment, but in this case, we're dealing with E. coli lysates. These were collected via data-dependent acquisition, which means that the instrument tried to produce tandem mass spectra from the most intense proteoform ions that were observed in the MS scan. And it was performed on a fusion instrument, a thermofusion. So we have a large number of spectra that have been collected. TopPIC and TopMG have already been run. Now, I'm going to include a link to the prior lecture where we demonstrated the use or the configuration of TopPIC for doing this search. But we are adding another search engine in this presentation so that we have two different tool sets from the same suite. So TopPIC is designed for identifying proteoforms at large, and TopMG is particularly good at recognizing post-translationally modified versions post-translationally modified proteoforms of those sequences. So I'm going to start by looking at how we ran the software. In this case, I did the operation using TopPIC Suite 1.5.3, which is the current version available today, but I doubt that this would change tremendously if we were to look at TopPIC Suite 1.4 or whatever comes after us in the future. So we started in this case by launching TopFD. TopFD is the feature detector and deconvolution engine of TopPIC Suite. And starting from MZML files, the software is able to deconvolute the precursor ions and the tandem mass spectra to reduce them all to singly charged state to prepare them for identification. In this case, I was running on a Linux computer, which is why the path has forward slashes rather than back. But the command line looks essentially identical whether we run it on Windows or on Linux. In this case, I was using a computer that had 6 processor cores, so I allowed it to use all 6 when doing the deconvolution. That step moves pretty quickly. I believe well within an hour, we were able to deconvolute all 3 of the raw files that we were going to use, or all 3 of the MZMLs in this case. Next, we launched TopPIC. Now, TopPIC, as I said, is kind of the mainline identifier within TopPIC Suite. It requires that you have run TopFD or another deconvolution engine ahead of time, and TopFD, having read MZMLs, is going to write MS-align files. MS-align files are very much like MGFs with some differences in the headers for each spectrum. Now, the command line for running TopPIC is quite a lot more complex, and if you've watched the demonstration before, you saw that I used the graphical user interface to launch the search. This search is almost identical to the one I performed before, but there are some small differences beyond the fact that I ran it in Linux. So TopPIC here was configured to use a -S2 search, which means that the software can allow for up to 2 regions of PTM mass shift between the spectrum that's predicted from a proteoform in the database and the spectrum that's observed on the mass spectrometer. So if you're allowing for PTMs to be present in your proteoforms, you either must use -S1 or -S2. In this case, by allowing for -S2, we're allowing for a little bit greater flexibility in finding post-translational modifications. Once again, we're going to allow the computer to use all 6 of its processor cores. If I were running this on my laptop, I would require it to use only 4 processor cores. And once again, we're going to use the option to make a conjoint report, which is to say one report that spans all of the input files. The software will still present its analysis of each raw file independently, but this -C option creates a single report that spans all of them. Importantly, we need to tell the software how to interpret the mass shifts that it observes. And in this case, we're doing that in a file called topptms.txt. I have that open down here at the bottom. You can see that most of this is commented out. That's what these little hash symbols mean at the start. Ignore this line, essentially. But those lines are useful because they explain how to interpret each line of each uncommented line of the file. So when we get down to the bottom, we see that these first three potential modifications are all commented out by that hash symbol, but the last two are going to be retained. So let's pay attention to those in particular. We're going to specify that oxidation is a modification with a mass of 15.9949 Daltons. It is located on methionine residues. They can occur anywhere within the protein sequence, and they have a number in Unimod of 35. This is just a way to be able to do the lookup for it within the software. Similarly, we're going to use disulfides as a modification. They result in the loss of two hydrogens when they take place. So when two cysteines form a disulfide, they go from being SH side groups to SS bonded. So the hydrogens have to leave, and for that we lose two mass units. It can occur on a cysteine. It can occur at any cysteine, and its index number within Unimod is 2020. So you probably already noticed something a little strange about how I did that definition. I specified that a single disulfide causes a loss of two mass units, but I didn't specify that it accounts for a pair of cysteines. I'm going to have the software just place it on one cysteine, and hopefully the other one will be close enough to this one that it doesn't matter too much that I've put all of the mass loss on one of the cysteines and not a pair of cysteines. So that's just something to keep in mind. So top PTMs, the text below, is what the software will use to define the PTMs in question. We're going to use a sequence database that's located at this location on my file system, and it's going to read in all the MS-Align files that start with 2 star. That start with 2. The star here just means that anything can take that place. So why would I specify that I only want to use MS-Align files that start with the digit 2? The reason here is that I'm creating a conjoint report. And part of that conjoint report is to create a single MS-Align file that covers all of the input MS-Aligns. So when I run this first tool, when I run TopPIC in the first place, it's going to read all of the 2-star MS-Align files and add a new MS-Align file called conjoint. So by specifying I only want to run on 2-star MS-Align files, I prevent myself from running a search against conjoint MS-Align in addition. TopMG is called very, very similarly, but we still see that we have this -U6 business. We're going to use all 6 CPUs. We're going to create a conjoint report that spans all of them. We're going to use the same definition of modifications, the same sequence database, and the same MS-Aligns as input. But this -P3 is kind of a different option. -P3 says that we're going to allow TopMG to include up to 3 PTMs in making any particular identification. And that's going to have some changes in what kinds of identifications it produces. The search itself is going to produce a huge number of files. I think I mentioned in my previous video about this that I typically run with an option called -G that prevents the software from making HTML output. That dramatically reduces the amount of reporting that the software does. If I look at this directory of reports, I'm showing you just the conjoint part of the reporting. I'm not showing you each raw file separately. And what you see is that we have feature files that represent the attempt to integrate an intensity for the MS1 features that serve as precursors to these tandem mass spectra. I have a bunch of files with TopMG in the name, a bunch of files with TopPIC in the name, and of course I have my script file that represents how I ran things in the first place, and the TopPTM's text file. Again, this is just a small part of the overall reporting. The reason I say that is I also have this big conjoint underscore HTML directory. This is the useful bit of reporting for people who want to have who want to interact with the data underlying their support their reports. Most of this other stuff represents tabular data. So I'm going to show you just a couple of those files. These are TSV files, conjoint MS2 TopPIC prisms, and conjoint MS2 TopMG prisms. Remember, I had to tell it I wanted to have a conjoint report using the -C option. If I leave that out, I wouldn't have these files to look at. But these tables are very useful because every row here should represent a different proteoform spectrum match made by either TopPIC or by TopMG. At the top of the file, we have the list of parameters, which is very useful if you've lost the command line you used to launch the software and you want to know how it was configured. So all that stuff appears up here at the top. And then finally down at the bottom, we get this large table showing all the information for every proteoform spectrum match. The same is true over in the TopMG report. Now, you probably noticed as I switched between windows that the configuration options are different between the two tools. They are quite different in how they proceed, so it's worth understanding how they differ. So I'm going to start by opening up this A column nice and wide. We can see that the sequence database we used, which spectrum file it represents, how many spectra were combined. We're getting a much fuller appreciation for all of the different configuration options. It's worth noting that in this case, I did not do a target decoy search. I included only sequences that are real potential matches for tandem mass spectra. We use the -S2 option. That means that the maximum number of unexpected modifications is 2. We have error tolerances. We see how the software is doing its filtering at the spectrum level and at the proteoform level. Because we didn't do a target decoy search, we only have the ability to cut off on E values, not on TDA-derived false discovery rates. We see that the software used its default option of allowing for N-termini to be intact or to have the initial methionine truncated, and it can be acetylated either in intact or methionine truncated form. We have a very wide window on how much mass may comprise one of these mass shifts. We said -U6, here that's shown as thread number 6. It's using the generating function to compute its e-values, and so on. And helpfully, it tells us which modifications are in play, along with what their names are and what amino acids they can occur on. Okay, so all of that should be relatively straightforward. We also get a little bit of runtime information. On this computer with 6 relatively old Xeon processor cores, we see that the search of 3 raw files took 7 hours to complete, from about 3 in the afternoon to about 10 at night. Okay, now that's very similar to what we see in TopMG, but remember that we had that -P3 feature in place. I want to walk through these where they differ a little more carefully. Again, no fixed modifications. We didn't use iodoacetamide to block free sulfides, so that's good. All right. Once again, we're doing just a target search. We're going to filter on e-values. All 4 possibilities for the N-termini are available. Maximum modification shifts, thread numbers. All this stuff looks pretty similar. But you see that we have a maximum number of variable PTMs. The software is saying that for an individual prism, no more than 3 PTMs are allowed to be made. That's the -P3 option showing up. And right here we see that the maximum number of unexpected modifications is set to 0. Now this is a really important way that TopMG differs from TopPIC. TopPIC is going to interpret any mass shift as an unexpected modification first, and if it can interpret that as one of your listed PTMs, it will. But in this case, we can actually enforce that any mass shift that cannot be accounted for by some combination of the defined modifications will be omitted from the search results. So TopPIC will output unknown mass shifts, and there's no way you can stop it from doing that except to turn off all PTM finding. But in TopMG, we can enforce that the only PTMs to be included in its PrSM list must be those that can be explained by listed PTMs in our top PTMs file. All right, so no unexpected mass shifts will be displayed in TopMG. Okay, how much time did we take to do this search in TopMG rather than TopPIC using the same sequence database, the same PTMs, and the same configuration overall? We see that this search started at about 7 a.m. in the morning and finished at about 2 in the afternoon. So although TopMG is generally speaking slower than TopPIC, if you cut down the number of PTMs low enough, you may get a search time that's very comparable. I would also note that this software defaults to 5 PTMs per PrSM rather than this 3. So I've already configured the software in a way that has cut its search time compared to what it would have been if we'd allowed for 5 PTMs per PrSM. And once again, we have this table of data below it. So just as a starting point, we might ask, did we identify more PrSMs with TopPIC than we did with TopMG? And one of the easiest things to do for that is to simply count the rows. Now, I want to caution that counting the rows can be a little bit dangerous if you're doing this in a mammalian database. And the reason for this is an important way that TopPIC 1.5 differs from TopPIC 1.4. In mammalian proteomes, you will frequently find that a given sequence can be explained by multiple accessions in the database. If, for example, you have a proteoform that covers a conserved part, a shared part of a gene that has multiple splice variants, multiple isoforms, you can find that each of those isoforms is listed as a different accession in the database. And so the same proteoform can be attributed to multiple accessions. In E. coli, that's much less likely to be a problem. But in this case, we do see that there are examples where this does happen. So here we see glutamate decarboxylase alpha and glutamase decarboxylase beta have very similar genes, but they appear as different accessions. And so this single proteoform would be counted twice if we simply count the rows. But the software is telling us by this mostly blank line that these 2 accessions both explain this proteoform. So we're going to have to just sort of ignore that step for now. And when we ask about sensitivity, we have to keep in mind there might be some amount of double counting that differs between the TopPIC and TopMG reports. So let's simply count how many rows we have. Oops, I've missed it again. All right. So I want to do a quick end down. Oh, I have to actually do one more thing, sorry. So I'm going to hold down Shift and now do end down. I missed it. Oh goodness. Well, it's a tall table, but we'll just sort of work our way through it. Tell you what, the easiest way to do this, I'm sorry, sometimes a bioinformaticist makes a mistake, is to simply remember there are 32 rows before the top of this table. So the table runs, I'm going to pull open a calculator if you don't mind. I have my calculator now. I'm now going to say the bottom of the table is row 8729. There are 32 rows at the top of the table. So there are 8,697 rows in this bottom table. That's the TopPIC result. So we can, to one approximation, we can say there's about 8,700 PrSMs here. However, remember that some of those are blank lines that represent cases where a PrSM is matched to multiple protein accessions. So when we pop over here, do we see the same result? First off, we have 29 rows appearing above this, so we're going to have to do the math a little differently. So we have only 3,518 rows here. So 3518 minus 29 is what we want. 18 minus 29. 3,489 prisms. Okay, so already we see that TopPIC has a much higher sensitivity. It's identifying roughly twice as many prisms as does TopMG. And that's important. It should remind you that anytime you increase your search space by looking for more modification variants, you have the it's quite likely that that increase in search space will drop your sensitivity. Now, if we were to run TopMG to allow for only 2 PTMs per prism, we might find its sensitivity improves quite a lot. But I want to share something important with you. TopPIC very frequently relies on proteoforms with unknown mass shifts in them as a way to improve its sensitivity. So what does that look like? If we were to look through this prism, for example, this is just one chosen at random, we see that its sequence truncates the initial methionine. It has a modification in the middle, and you see it is not labeled as an oxidation nor as a disulfide. In this case, the software believes that some PTM of negative 1.75 Daltons is found somewhere in this parenthetical region. That's not a named mass shift. That's an unknown mass shift. So TopPIC is using identifications like that to boost identification sensitivity by quite a lot. So can we fix this? Yes, you can adjust for that. You see that one of the fields exported by TopPIC is unexpected modifications. So in this case, I want to sort on column X to tell me just how many of these there are. All right, so using the data sort option in Excel, you can obviously do this with any spreadsheet you like, or do it in R using the subset command. I'm going to just sort from smallest to largest. So how many of these prisms have 0 unexpected modifications? Okay, and for this, we can just drop down, down. We're going to have to do this for quite a while because there are a lot of these unmodified prisms, and that is very, very good news. I didn't actually look up this number first, so I'm going to be as surprised as you are to determine what that number is. We're already at 2,000 proteoforms identified with no unknown modifications, so that's good news. More than 3,000, good news. Oh, we skipped it, there it is. All right, so if I can just move up to that boundary, here we are. We see that there are, here's the count, 3,750 prisms created by TopPIC that contain no unknown modifications. Over in TopMG, the total number of prisms was 3,489, 3,489 versus 3,750. So the apparent sensitivity gain in TopPIC is relying heavily on these unknown modifications. Now, just because something has no unknown modifications, does that mean that it contains no modifications? Well, here we see an example pretty early on that has an acetylated N-terminus. If I pop up to the top of this table, I can see that, yes, we're seeing things like oxidations, and some of these are going to have disulfides as well. You can actually see what those are a little more readily if you pop open this MI score column. Here's one with both oxidations and disulfides. So here we see that this sequence stretches all the way from the start of the proteoform, the start of the accessions sequence to the end of the accessions sequence. The N-terminus is oxidized, and there's a cysteine in the middle that is carrying a disulfide. Okay, so yes, it is possible to separate TopPIC's identifications with no unknown modifications from those that do contain unknown modifications. But if you do that, you will find that the sensitivity afforded by the algorithm drops quite a lot. The software is designed to give you these identifications and always include unknown mass shifts as a result. All right, so we would like to do a little bit more to pin down how we interpret these identifications. We've already mentioned a couple of the factors that come into this, but I think there's a bit more that we could do. I'm going to change how we're sorting these data. I'm going to leave the unexpected modifications. I'm going to keep those pushed out of this list. But now I'm going to sort on the basis of the accession, the protein accession data, and I'm going to sort on e-value. Okay, e-value is back here at the end, and I'm going to want the smallest to the largest. The accessions are going to be sorted in alphabetical order. Mostly, I just want to have all the prisms for each accession pushed together into one clump. But then I'm going to sort within the protein accession to have the lowest e-values at the top. Remember that the lower the e-value, the better. An e-value here is attempting to say, out of all possible sequences, how many of possible sequences would we expect to have a lower score than this, than the best one that was achieved for this spectrum. Okay, and when we get to this, we see that our accessions, I'm going to highlight that column, that our accessions are all grouped together. We see that there are, for example, all of these different prisms observed for fumarate reductase flavoprotein. So we can ask things like, are all of the proteoforms that we see for one accession identical? In this case, all of these spectra are identical. Now I want to note that the input data in this case were 3 technical replicates. So we expect a degree of duplication to occur within each raw, across these 3 raw files. We might ask, are these 1, 2, 3, 4, 5, 6 prisms all from the same input file? If we pop to the left, we see that the first 6, we had 2 from replicate 12, we had 2 from replicate 10, and we had 2 from replicate 11. So in this case, the 6 identifications for this accession were spread evenly across our 3 raw files. Further, we see that all of them had very similar, had identical proteoform masses. This is a theoretical mass derived from these sequences. Exactly the same sequence was found to match to spectra for these 6 spectra. Now, we might ask, how do those differ from the precursor masses that were computed? And one of that, we have the precursor mass here, the adjusted precursor mass here. And, we see that different charges were identified, ranging from 5 to 7. You might ask, why do we have these precursor masses disagreeing by a mass unit in some cases? And I would simply state that it's kind of difficult when you have a precursor charged as high as 7 to make sure that you know what the monoisotopic mass should be for each of these precursors. So to the software, getting the precursor mass wrong by 1 mass unit is no news at all. That's a very ordinary thing to happen. So the adjusted precursor mass is taking that that 1 Dalton error into account and adjusting it to this. We could then compare these adjusted precursor masses. We can compare the experimentally derived precursor mass to the one for the proteoform itself. Okay, which is also shown over here. I believe that these values and those in column J are identical. So that's all grand, but we're also quite interested in understanding other aspects of this. So what was the amino acid before this proteoform? Well, it's a D. Was that the first amino acid of the sequence in the database? I'm not actually sure. I would need to look at that because this is not, oh, I'm sorry, here it is right here. The software is reporting that this proteoform spans between residue 560 of the fumarate sequence to the last residue being 602. So the fact that the software is showing nothing after that second dot suggests to me that this is a C-terminal proteoform that's been clipped from the larger sequence. All right, so we pop down here. Let us move to another sequence that might be of a little more challenge to interpret. I'm going to look at the MI score as a way to kind of highlight those. Let's take a really simple case first. I hope that meets with everybody's hopes. So I want to note that right here we see that there's no dot shown at the end of this proteoform, which suggests to me that Excel is hiding the full sequence from us. It's using this square bracket as a way to indicate, as something to say it's okay for me to break the line here. If you look at the actual cell, you see that what it shows up here is not everything that appears down here in the cell itself. So the full proteoform is actually much longer than what you can see up here. But it should be plain, in this case, that the software saw a mass shift at the location of this methionine, and it has now interpreted that as a gain of 15.9949 Daltons that it interprets as an oxidation. So we can ask, is there ambiguity about where that is located? And the software in this case believes that basically all of the probability says that this oxidation must be on this methionine and no other. Now, if we look at the sequence, we see that there are other methionines in the sequence. Where would the next one be? There's not one just in terminal of that. And we'd really have to look a little further. So in this case, there's no other methionine in the neighborhood. The software feels very comfortable saying that this oxidation is located at this methionine and no other. That's why it gives this 99.9% probability to that localization. It is not necessarily the case that that's where it is, but that's where the preponderance of the evidence for this spectrum would place it. So when you see that that only one amino acid is enclosed in the parentheses before the PTM name, that's your indication that there's a very strong localization of this mass shift to this location. Let's look at one that's a bit more complex, though. All right, here we have one that's a little bit more fun. All right, now we have a proteoform in which oxidation is thought to exist somewhere in this region. When you tell TopPIC that it's allowed to add oxidation to a methionine, it knows that this is a modifiable site and this is a modifiable site. It believes that this modification falls within this parenthetical region, but it's not actually sure whether it falls on this methionine or on this methionine. By the way the software reports modifications, it might also seem that L, E, or H is a location for this oxidation, but that's not really how the software sees it. It's only allowed, in this case, to place the modification on the methionine at position 29 or the methionine at position 33. And it doesn't really have any evidence. There are no fragment ions that allow it to differentiate between these two locations. As a result, it splits up that probability to 50% on this location or 50% on this location. That's why it gives us that report. If we drop down a little further, we may find an example of a methionine where there is some ability to pin it down to one location or the other. we do see a few cases where that oxidation has been placed in one location, and yet it doesn't get a 99% probability of localization. Here we see a 92%. So the software believes that this is the best location to localize that oxidation, but it estimates there's an 8% chance that it would instead be located over at this other methionine. That it's not outside of possibility that it also be that the oxidation instead be N-terminal to it. There's some evidence to support other localizations here, even though it's only put this single methionine in the within the parentheses. And sometimes you have a really, really messy situation. In this case, the region within the parentheses contains 3 different methionines, and you see that all of them get a 33.3% chance of that oxidation sitting on it. So the software has no fragment ions in this case to tell it which of those 3 locations is best for housing that mass shift. Okay, so oxidations are a relatively easy way to talk about PTMs because we know very well where they should be. The disulfides, as I said, are going to be a little messier for us to play with because the mass shift attributable to them is actually found on 2 different cysteines. So in this case, the disulfide mass, the loss of 2 hydrogens, is shown to be on this cysteine. That by itself, I think, is not very controversial, except that we need to find another cysteine, hopefully very close by, that allows for this to be an internal disulfide where a -2 is attributable to the whole protein. So if I look N-terminal to this cysteine, I'm looking for a cysteine, and I don't see one. Maybe it's just my eyes, but I'm not seeing one. If I look C-terminal to it, do I find another cysteine? I don't. So this is a problem. The software claims that a disulfide is present, but there is no other cysteine to make this an internal disulfide. So this is an error. The software is claiming a disulfide is present when it isn't, because we told it to look for a -2 mass shift on any cysteine, and so it did. We know that this is an erroneous identification because there is no other cysteine for it to bridge to. But we have to think about how we should interpret this if this is an incorrect identification. And I would note that this is one case where making a mass error for the precursor, allowing for being off by 2 for the precursor mass, would allow us to have a mass shift that looks like we need to introduce a disulfide to match it. So that's not great. We see that all around this prism, these are all identifications to RL27 E. coli, and almost all of them have expected masses of 8987.841. Here we have one that's 8985.825. That 5 versus 7 means that this spectrum was misidentified because the mass error for the precursor allowed it to be matched to a disulfide variant that isn't possible. Okay, so good to be on the lookout for those because big swings in precursor mass are certainly possible when you have ions that are very large, and 9,000 is not tiny. Okay, disulfides. Well, that was an important case. This is one, remember that TopPIC was configured to allow for up to 2 regions of mismatch that can be explained by these modifications. In this case, running it -S2 allowed it to find an oxidation at the N-terminus of the proteoform and further on into its body. So in this case, a methionine that's internal to the proteoform and one that appears at its N-terminus both carry oxidations. Okay, so yes, you can find multiply modified proteoforms with TopPIC. but that's allowing, there is no -S3 option. You can't look for 3 regions of mismatch and thus 3 modifications all within the same search. That's really what TopMG is for. Now, remember we had a bit lower identification sensitivity, but roughly equivalent sensitivity when we left out the unknown mass shifts. So I'm going to do the same trick of sorting by proteoform, the protein accession, and then sorting by the E value. All right, the E value is back at the back end of this table. All right, so now we should have our accessions in more or less alphabetical order. I'm going to highlight that column just to remind me where it lies. And I think I'll broaden it out so we can look at those names a little more broadly. Okay, once again, fumarate reductase flavoprotein shows up here at the top. That's all grand. I think something I should have pointed out a while back was that this scan column is something that you're probably going to be looking for. Very often you want to know which tandem mass spectrum from this raw file matched to this proteoform. And both TopMG and TopPIC put that in column E. You might think, oh, I need the PrSM ID number or maybe the proteoform number. Don't look at those. The one you want to determine which scan number from this raw file is column E. So just keep that one in memory when you come to interpret these yourself. All right, we are no longer allowing any unknown mass shift to fall in our identifications. We don't have to sort those away in this report. But I wanted to note that the number of variable modifications is frequently going to make this a little interesting for us to interpret. So I'm going to pull open the MI scores didn't actually get computed. That's very weird. That's okay. We will just work our way through as well as we can. We see that some of the proteoforms that we're seeing are multiply modified. They have, in this case, 2 variable modifications that are reported. And you can see that TopMG in its proteoform reporting uses essentially the same kind of notation as TopPIC does. Here it is specified there's a disulfide present and an oxidation present. But I want to note that even though we told it oxidation can only happen on methionine and disulfides can only happen on cysteines, the software is including quite a range of potential locations where this disulfide could take place. The disulfide could occur on a glutamic acid, on a glycine, on a cysteine, on an arginine, on a glycine. That's rather weird if you ask me. The software is asking essentially, does it have fragment evidence to prove that it's on this cysteine rather than on these other amino acids? But we disallowed disulfide from being on anything other than cysteine. So I'm going to say that there are probably going to be some changes to these localizations in how they're reported within TopMG. I think that TopPIC, being kind of the named tool that TopPIC Suite is named after, gets a lot more attention on its PTM recording. And I know that they did a lot of work on it when they moved to version 1.5 from 1.4. So where TopPIC is applying a lot of tight constraints on where these modifications may be found and specifying that it could only be on this cysteine or that cysteine, and allowing the region of ambiguity to span the S and K as well, is actually a much more sensible way to talk about the locations of these PTMs than are these the notation currently used by TopMG. One of the things we might ask is, did TopPIC ever find more than 2 variable PTMs for a given peptide? Given a given proteoform. For this, I'm going to throw away these this three-level sort, and instead sort just on number of variable PTMs, and I'll add one more level. Within that, I'm going to sort on e-value. Okay, so I'm going to drop to the bottom of this report, and I see that the highest number of variable PTMs ever seen is 2. I ran the TopPIC software in -S2 mode, and here we see that the outcome has been that it will in no case find more than 2 PTMs per peptide. What about TopMG? Remember, we set it in P3 mode, allowing for up to 3 modifications. Here I can sort on variable PTMs, smallest to largest. Here it is, there's the column. And now I'm going to drop to the bottom, and I see that yes, indeed, the software, by being able to look for up to 3 PTMs, indeed found multiple proteoforms where that happened. So this is the best scoring 3 PTM PrSM that was created by the software. So what was the result for it? It's kind of an odd result when we look at it. We see that in this region, the software sees 1 oxidation and 2 disulfides. So that's possible. It could be that we have 4 cysteines within this region, and the pairs are individually disulfided together, and then there's also a methionine that is oxidized. So does that match up? 1 cysteine, 2 cysteines, 3 cysteines, 4 cysteines, and 1 methionine. I think that in this case, it is plausible that yes, there are 2 internal disulfides and an oxidation that all fall within this region. But we see that the software is going to require us to do the detective work of which one is most plausible as we interpret it. If we drop down to the next one, we see that again, it's an oxidation disulfide. Here we have an oxidation disulfide oxidation. Here we have a disulfide, an oxidation, and a disulfide, an oxidation, and an oxidation, and so on. So yes, it is certainly plausible that we can go searching for triple or quadruple or quintuple variable modifications with TopMG. But as it finds more and more PTMs, we're going to have to put in more and more detective work to interpret that. Okay, now I've spent a tremendous amount of time just on interpreting these 2 reports, and there's actually something that's a lot more intuitive, I think, for everyone to look at, that actually accounts for almost all of the files. Now, you know that I said typically when I run TopPIC and TopMG, I do not allow it to report to HTML. The reason for that is that the HTML reports are really, really big. If I do a quick properties on this folder, I can see that my conjoint folder containing TopPIC and TopMG reports, both in one folder for the same 3 raw files, is 17 gigabytes. That is large, and if you're trying to store this on a laptop hard drive, you might be a little disappointed by how much space that's taking up. So when I run TopPIC and TopMG, I always run with the -G option to prevent those from being reported. However, it's quite likely that you want that report if you're trying to report something that you will show in a paper. So it's important that you understand how to interpret those. It may seem when you open the conjoint HTML report that there's no HTML in here to look at. So I'm going to just tell you right away that the place to find the top the top level reporting that covers all the HTML you're going to look at, you want the top MSV folder. I pop in there and I see something called index HTML. That's the place where I want to start. So I will now open index HTML and up pops my browser. We see that top MSV is already designed at a high level to allow us to look at the identifications from TopPIC and TopMG. The software will always expect that both of those reports are present And if you haven't run TopMG, just don't click on this option down here because there won't be anything to see. But we can go ahead to open our TopPIC identifications. I'm sorry, in this case, I specified that I wanted to look at prisms, at spectra that have been identified, rather than at proteoforms themselves. So I look at my prisms list, and I see that 234 different accessions, just called proteins, are identified. So already the software is doing some summarization to help me interpret that. And I see that my proteoforms have been sorted by which protein, which accession they relate to. So if I drop down, I expect to see a total of 234 different accessions reported. And the software is reporting what is the best prism that I've seen for each one. Now I'm going to do a little bit of sleight of hand. I'm going to open my TopPIC results. That's interesting. I'm going to have one tab open that looks at TopPIC results. And I'm going to have another tab open that looks at my TopMG results. Okay, so we identified about twice as many spectra in TopPIC because it's including, in this case, the unknown modifications that it identified. And yet the number of proteins we identified is much smaller when we look at TopPIC than we look at when we look at TopMG. 730 proteins versus 234 proteins. Are the error rates controlled the same way? In this case, we've told TopPIC and TopMG to control their error rates at 0.01 at the prism level, the proteoform spectrum match level, and also a 0.01 at the proteoform level. So those are being applied the same. The effective false discovery rates, however, may be different, especially once we remove the unknown mass shifts from TopPIC. So the number of proteins is higher in TopMG than in TopPIC, using the same e-value filtering in both. So let's look at this top protein seen for TopMSV, RL36 E. coli. All right, RL36 E. coli, here we are. So P0A7Q6. If I click into this, we're now looking at the same accession for both. We see that 3 different proteoforms were observed by TopMG. 31 proteoforms, on the other hand, were detected by TopPIC for the same proteoform. It's a little weird, isn't it? Is the number of spectra that we saw for it different? Yes, in all likelihood, it was. So these are 2 very different search algorithms, even though they're working from exactly the same databases and the same, importantly, the same deconvolutions of the same input data. So we're able to look through this and ask whether the proteoforms we see are conserved between the 2. Here we see that this proteoform stretches from 1 to 31, 2, 3, 4, 5, 6, 7, 8. It's a 38 amino acid proteoform with a disulfide appearing up top. Was that the best one here? M to G. This appears to be the same sequence. M to QG, yeah, same sequence in both. In this case, the best proteoform has a mass shift of 32 on it. How could we see a plus 32 here? Well, one way that we could plausibly interpret that is that we have a double oxidation on it. But the double oxidation doesn't seem very plausible. We have no methionines here, except this one all the way up at the N-terminus. Maybe there's a double oxidation event, however, that has taken place on cysteine. I did not allow TopPIC to put a mass shift of plus 16 or plus 32 on cysteine, but cysteine can carry oxidations. So it's plausible that this is a real thing, even though it's an unknown mass shift here. But clearly, that's not what we saw in TopMG. Instead, its best scorer was a disulfide bond on probably these two cysteines. Okay, so did we see that one over here? If we scroll down a bit here, proteoform 443 has a mass shift of 305. I don't know what that is. Proteoform 470 shows a disulfide at, I believe, the same location as the other one did. We still stretch from MK to QG for our proteoform, MK to QG for the proteoform. Here we saw 35 prisms where we saw a disulfide including that cysteine. How many spectra did we see for this up here? Well, pretty comparable, really. The same proteoform with a disulfide on that includes the cysteine had 40 prisms from TopPIC and had 35 prisms from TopMG. If we were to dig through those, we would probably find that the scan numbers are quite similar, have a strong overlap between the two. So let's try that. I'm going to drill into this and look for the prisms for TopMG and the prisms for TopPIC. Now, the software is doing a bit of sleight of hand here. You can see that it's reporting scan numbers, but it is not showing us which raw file these relate to. So that bothers me. I did 3 different raw files here, and I can't tell which one contributed each of these scans. If I click into it further, I get the raw file name out. So this first one is replicate number 10 with scan number 1769. Can I find that same one here? 1769. I think this could be it. I click over here, and I see I'm on replicate 10, scan number 1769. So this is good news. We're seeing the same spectra get matched to the same spectrum being matched to the same proteoform by these two algorithms. That's really, really good news. We should not expect, however, that every prism for this proteoform in TopPIC matches to a corresponding prism from TopMG. Similarly, you might assume that because more spectra were identified to this proteoform by TopPIC, that most of the prisms seen in TopMG are also identified in TopPIC. But I'm going to wager that at least some of the spectra identified by TopMG to this proteoform are not identified to this by TopPIC. It's a little vexing, but this does in fact happen. So there are 40 in TopPIC and 35 in TopMG, and they have some sort of Venn overlap, but there's going to be some prisms identified by each search engine that are not also identified by the other. Okay, let's now look more closely at a TopPIC proteoform. I'm just going to choose this top one because I'm sure it's just fine. I can get a lot of information about which peaks within the tandem mass spectrum are matched to this proteoform. If I click just the matched peaks, I can see that this is the C35 ion, the C36, the C32, and so on, the Z double prime 36. These are ETD spectra, so it makes perfectly good sense that these would be identified that way. But I might want to look at the spectrum itself to see how that relates to it. Okay, so now I am looking at M over Z values and how they relate to it. It is possible this is one of the reasons why the number of files created for these reports are so huge. Each spectrum is represented as a JavaScript object that allows us to do a close-up examination of these spectra. But I'm being kludgy today, so I'm not sure I'm going to be able to show all of that. So here we are able to do this interrogation of these spectra and look at them up close and personal. So that's rather lovely. Here we go. So now we have a spectrum viewer. We can even do things like, oh well, it doesn't like my PTM names. That's okay. It even allows us to play what if games. What if we change a modification so that it's no longer there? change our interpretation of where the PTMs are located, etc. So. Okay, so that's quite a lot of information. This hopefully has given you some sort of introduction to how we can interpret TopPIC and TopMG searches and look at the results at a very high level, or look at an individual PrSM close up. I should mention that although I tend to be most interested in which spectra are identified to a proteoform, I'm also quite interested in being able to look at a proteoform level. So being able, this interface allows us to be able to look at a proteoform level where the spectra data are summarized by which spectra they match to, etc. Which PrSMs match to which proteoforms. And once again, those results are going to be a little different. Here we're not asking about how many spectra are matched to a given accession, but rather how many proteoforms, how many distinct truncations of sequence and combinations of PTMs we've observed. All of that is possible within this interface, and hopefully the software makes it possible to jump directly to the best scoring of the proteoforms as well. So there's a lot of power in these reports. Now, I would stress that it's probably a very good idea for you to leave these files zipped up rather than keeping them extracted in that way. And I'll try to explain why here. I already did a quick look at just how large these directories of files are. In this case, we see that we have 17.4 gigabytes of HTML and text showing up within that directory. That's quite a lot. Compare that to the file, to this tar.gz file that represents all of those files stuck together and compressed once. Here you can see that in 1.5 gigabytes, I'm able to store what would be 17.5 gigabytes on disk. That's kind of a surprising factor for a lot of folks, but the reality is that HTML and JavaScript and text objects all zip up really, really well. So you could use something like 7-zip to shrink these all up to a file under Windows and keep the report for posterity, but not have it taking up a huge amount of space on your file system as well. Okay, well, my voice is giving out, and I've covered the main points that I wanted to cover, but I hope that you feel a little better prepared for interpreting PrSMs and proteoforms produced by TopPIC and by TopMG using their excellent HTML output, or looking at the tables that their software produces. And with that, I'll call this quits. Thank you very much for taking a look. By all means, look around the YouTube channel for other videos that you might find interesting about top-down proteomics or bioinformatics in general. Thank you.